All right. I hope you survived the last 2 lectures, and I'm assuming the topics that needed to be covered were covered. So I'm not, I have not received any note contrary to that. So we have a few residual lectures. Some of them are, they may sound a little bit of a review, but hopefully we will do some new things in between. And today I wanted to just go back to undirected graphical models, because basically they are the graphical models of more importance for scientific applications. Okay, so we need to cover a few things in details. Reminders, not next week, next week, all the presentations in the class are going to start, and I'm going to be randomly picking names. I'm saying you, and you today, you tomorrow. Okay? So don't send me a request and say, please, can I speak the last? Can I do this? Can I do that? And I think your presentations, it would be useful if they are due a day before you actually speak. The papers, we can make them to be due basically at the end of the semester. So that way you have a few more weeks to write the actual 6 pages. Okay? But there's no point of giving a presentation and then say, please see a revised presentation. Of course, if the presentation and the paper don't agree in content, we're in trouble. Okay? So don't bother basically submitting them if they're not on the same frequency. Now, next week is the SciM UQ meeting. I am not going to be here. I have no idea if Suvik is going to be here. So we may have a lecture on Friday, if I make it on time, but for sure I'm not here Tuesday and Thursday. Okay? All right. So actually, for this will be most probably more than 1 lecture. I don't know how much we're going to cover today. The plan is for 3 lectures, but I think I don't have that luxury, so a maximum of 2 lectures. This follows chapter 19 from Murphy's book, and also chapters 4 and 7 from Kollers and Friedman PGM book. Okay, so they are both excellent reads. All right. And as I said, for those who work in science and engineering, this is a very relevant topic. So let me give you a few basic reminders, and we'll try to revisit a few concepts. So what you see on the top is an example of a directed graph, all right? And on the bottom we see an undirected version of this, where you notice we have done what? What's the buzzword? What it is? Moralization. So we have moralized the parents. So for example, 7 has 3 parents, right? And you notice 4, 5, and 6, basically we link them. Similarly, 5 has 2 parents, 2 and 3, and we marry them. Now we will see that when you moralize, it doesn't by any way imply that whatever conditional independence relations you have for the graph on the top, you're going to have the same relations on the graph on the bottom, and this can be an issue. I mean, it's easier to work with this model, right? And today we're actually going to be talking about undirected graphs, okay? So there is a merit to do this, but you need to be aware that the conditional relations here, they're not the same as the ones on the bottom. Not always. All right? So why do we need to understand undirected graphical models? The easiest example, think that the nodes, the random variables in your graph are, let's say, the pixel values in an image. It doesn't make a sense to actually put directions. What does directions mean in an image, right? That this pixel affects is the parent of that pixel, and that is the child of that pixel. What does that mean? It doesn't mean anything. So really, there is no meaning to actually use a directed graphical model, let's say, in the context of image analysis. And more importantly, it's not relevant to use it in this huge field of spatial statistics. Okay? where you effectively try to model correlations in a spatial domain. So I'll give you an example and to indicate basically how different things can be between directed graphical models and undirected graphical models. So let's concentrate on node 8. Okay, so this is like a, you can think of this as an image, and these are the pixel values, right, which we take them to be random. And let's say we put some arrows the way that you see here on this grid. Okay, so we look on node X8. Can you tell me, just looking at this graph, all of these other nodes that you see there, all together, what are they? Can we assign them a name in the context of the node X8, and why? So look very carefully. All of these nodes, right, that surround X8, except of course, I can see here X2, right? If we lump them all together, what are they in the context of X8? The Markov blanket, okay? So the Markov blanket here includes the parents, includes the children, and what are X12 and X4? The co-parents, okay? X2 obviously is not included, right? So the idea here obviously of the Markov blanket is that if we know the values of the Markov blanket of this node X8, then X8 is conditionally independent of anything else in the graph, okay? So obviously you have to look very carefully on this grid here to say, yes, this is the Markov blanket, but X2 is not included, X14 is not included, okay? So let's look now the undirected graph. Will you agree with me that the Markov blanket is only those 4 nodes? The neighbors? Because you remember conditional independence basically in an undirected graph is defined by the neighbors. So if you describe the values of these neighbors, right, X8 is independent of anything else, because if you think of this operation, to go from X8 to any other node, you have to go through these neighbors, this Markov blanket, and if these are observed, you're blocked. Okay? So point is, this conditional independence relations in the context of undirected graphs are way simpler than what you see with a directed graph. So obviously there is a merit to actually work with undirected graphs. So a few buzzwords as to advantages and disadvantages. So the undirected graphs are symmetric. You notice when you look, for example, for the neighbors, it's not like this is the father, there's no orientation, this is the kids, these are the co-parents. You don't have anything like that. Everything around the node is symmetric, all right? So in the context of spatial statistics, that's very relevant. We will see, if not today, on Thursday, that when you discuss discriminative analysis, or when you try to produce models, P of y given x, and this we will do this in the context of conditional random fields. Undirected graphical models are very appropriate. This is very difficult to do with directed graphical models. However, there are disadvantages in, you remember, and we will revisit this today, the parametrization of the joint probability distribution in directed graphical models in terms of clicks, right, has no physical meaning. They're not like probabilities, So you cannot really interpret things as easy as you do with directed graphical models. And the parameters that are involved in the clicks are very difficult to compute. So the algorithms are a little bit more complicated. Even, and again, we may see this today or on Thursday, when you work with directed graphical models, and lots of the local probabilities, like the probability of a node given its parents, are normalized. This is not the case for undirected graphical models. So the normalization requires actually to work with all the clicks everywhere, and that is a very computationally difficult problem. Okay? Actually, most of the algorithms have difficulties just because of computing properly the normalization factor. All right. So in undirected graphs, the only conditional relation that we basically have played with is what you see here defined with this separation. So XA is independent of XB given XC, right? When any path from XA to XB has to go through XC, okay? And this is what we call a global Markov property, right? So for example, if you look at nodes 1 and 2 and 6 and 7, they're condition independent from, 1, 2, and 6, 7 are condition independent given 3, 4, and 5, because to go from 1 or 2 to 6 or 7, every path has to go through 3, 5, and 4, so that's the global Markov property. This local Markov property is basically defined in terms of the immediate neighbors of a node. So if you fix the immediate neighbors, that's the Markov blanket. Basically, this node becomes separated from all the other nodes. Okay, so this is the local property. So you just look at the nodes of, at the neighbors of a node. And then there is, okay, so here's one example. One is, so given 2 and 3, 1 is independent of all the other nodes, all right? Because, again, 2 and 3 are the neighbors of 1. Once you block them, there's no path to go from 1 to anywhere else. And then you have this pairwise Markov property, all right? So, if here's again your neighbors. So 2 nodes are conditionally independent given the rest if there is no direct edge between them. Okay? 2 nodes are conditionally independent given the rest, all right? If there is no edge between them. Can you see that? If the idea again of this separation is, so let's say I'm looking at 2 nodes, X8 and X9, and all the other nodes are fixed, all right? Obviously, there is a path from X8 to X9 on this plot, all right? So the only way you can make this independent if there is no link, and that's why this is called a pairwise Markov property. So for example, is X7 and X13 independent given everything else? Is X7 and X13 independent given all the other nodes? Yes or no? Yes. Okay. All right. So what is important, and the proof is given in the big Bible on probabilistic graphical models by Color, that all of these properties, the global properties, the pairwise and the local property, they're all equivalent. So if you start with one, you can show the other two. It's not an obvious theorem, and the proof is it's not very tricky, but not well. I believe actually somewhere I read that it was never formally published anywhere, but it's given in the book that you can read. All right. So why do we, I mentioned in the beginning that conditional independence relations between, when you normalize the graph, basically, you don't maintain the same conditional independent relations between the directed and undirected graph. And the key example is a directed graph that looks like this. Okay? You remember this fork example, the explaining away, and the undirected version that looks like that. Okay? So, for example, on this graph, right, with this separation, if you fix B, there's no path from A to C, so A and C are independent. Here, if you fix B, A and C become conditionally independent. You remember? So if you don't know B, A and C are independent, but if you know B, all right, A and C compete to explain B, okay, and that's where the dependence comes. So immediately you can see that these conditional independence relations are not the same between a directed and sort of the equivalent directed graph. All right. So we do moralization, and I'm going to show you that actually moralization does not maintain the conditional independent properties of the directed graph. So let's briefly see this. Look at this directed graph and the corresponding moralized undirected graph. So will you agree with me that given 2, where it's 2 given 2, 4 and 5, all right, given 2, 4 and 5 are conditionally independent, right? Okay, so let's look here. Given 2, 4 and 5 are not conditionally independent. Why is that? Because you can actually go to 5 through 6. You remember conditional independence relations on direct graphs is this, how do we call this, ball, what was Davis ball experiment, right? So you can actually, if you go to 5 through 6, right, nothing is blocked. So 4 is not independent of 5. Now, is there any way we can actually fix this and make sort of this graph to have sort of similar conditional independence relations with an undirected version? And the answer is yes. So let's look at this example with a little bit more detail here, right? So it says, given 2, 4 and 5, they're not independent, okay? Now, what is in this diagram that makes this relation to be destroyed? Can you look sort of tell me what link in that undirected graph is responsible for violating this independent relation? In other words, what did we do during moralization that somehow resulted on 5 not being independent of 5 given, or 4 not being independent of 5 given 2? Which link is there that created the problems? Say it again? The parents of 7, you mean 4 and 6. All right. So you may say, why bother to introduce? So you remember that this came basically, looking at 7 and say, okay, 7 has all these parents, let's marry them. But I don't see any 7 in this conditional independence relation. It's not like when we write this, we say, n given 7, do this. 7 is not coming in. So if we somehow concentrate only on the nodes that are of interest here, maybe we'll avoid moralizing 4 and 6, and then this conditional independence relation that we have on the left will also be applied. So here's what you need to do. If you want to prove a conditional independence of, let's say, of A and B given C, you form what is called the ancestral graph, where you only keep, so you start with a directed graph that only has the nodes A, B, and C, nothing else. Okay? So then you moralize this graph, all right? And then you can show actually in our particular case. So let's see. In our case, we're interested really on nodes 2, 4, and 5. Certainly 6 and 7 is not there. So there's no need to actually, to put 6 and 7 in the picture at all. All right, so we don't have any 6 and 7. So, so you can see now if you moralize this, all right, this relation is actually true. Is that the case? Given 2 is 4 independent of 5. All right, so again, if you restrain yourself on the ancestral graph, all right, in this case, the union of A and B and C, you can maintain the conditional independence relations on the directed and undirected graph. All right. Some homework in early lectures we define basically a graph being an I map of a distribution if the independence relations implied by the graph are subsets of the independent relations implied by the distribution. And we also define a perfect map. So G is a perfect map of a distribution if I of G equal to I of P. The message here is that the directed and undirected graphs are perfect maps basically for different sets of distributions. Okay? In this sense, they are powerful, but basically they are complemental of each other, right? Complementary of each other. So let me give you an example. I think this was in an earlier lecture, but we make an effort to avoid discussing all the details. So let's consider this undirected graph, all right? And can you give me some independent statements on this graph? Simply by looking at this separation. So A is independent of C, given what? D and B, because every path is blocked by D and B, and similarly, D and B are condition independent given A and C. So the question that someone may ask is there any directed graph that encodes exactly the same independence relations as this undirected graph? The answer is you can try. The answer is no, and what I demonstrate here is two examples. You can try as many as you want. All right, so let's design this directed graph. So first we can see that A and C are independent given B and B. That's nice. You see that? Okay? So A and C independent given B and D, which is the same as that. But let's look at another relation that actually is implied by this graph. Given A, B and D are conditionally independent. You see that? So given A here, is B and D independent? Given A, is B and D independent? No, why? Because there is a path to D from B through C. Okay? So this doesn't work. Let's look at this graph. We satisfy, given B and D, A and C are independent. All right? So this is the same relation as there. So let's concentrate on this independent relation that says that given nothing, B is independent of D. Why is that? That's obvious, isn't it? All right? So B is independent of D. I mean, there's no such a thing, B independent of D there. Okay? So you can try other cases, right? You can convince yourself that directed graphical models don't basically have the same independence relations, and the majority of the issues basically are coming from the fact of this explaining away scenario that we have seen earlier in the course. So basically what as a conclusion, if you take the whole subset of probabilistic graphical models, okay, this is the directed graphical models, all right, with their condition independence relations, the undirected graphical models, and there is a subset of directed and undirected that they're called Chordal graphical models that basically say the same condition independence relations, and those Chordal graphical models are really models that somehow the graph, if you lump variables together in cliques, you get a tree, the same way when we work with the junction tree algorithm. All right, so there is a relation there. That's why the junction tree algorithm is successful. So a Chordal graph is a graph where if you collapse the variables in each clique together in mega variables, what you get is you get a tree. Okay, so apart from that, there is a whole subset basically of conditional independence relations that you can get with directed graphs that you will never get with undirected graphs. All right, so let's discuss about the parametrization. So the parametrization we discuss, it has to be in terms of potentials defined over the cliques. So these potentials, each of them is parameterized with a set of parameters theta c. So this is potential on clique C. These potentials capture basically locally dependence between variables, but they are not probabilities. Okay? So you cannot really say much about working alone on this potential. You cannot basically do inference, because to do inference you will need to put the whole joint distribution with all the potential terms together. So this is the most famous theorem, actually, the Hammersley-Clifford theorem, that says that the joint distribution of all these variables y in a direct graph is the product of potentials defined over maximal clicks divided by a normalization constant, this partition function. Theta are the parameters defined over each click. Okay, this decomposition is not unique, and so for example, if you have potentials here that they are pair potentials and you have sort of evidence potentials for each node, you can lump them together to pair potentials. So this decomposition is not unique. As a matter of fact, when you write algorithms, you may want to make this decomposition as any way that you think is going to simplify your type of calculations. Now, the difficult thing here, and if I have time, we will discuss it today, otherwise on Thursday, is computing these parameters theta. And you notice, unfortunately, you won't be able to do inference locally in general. You will have to, this term here, this partition function, is that links everything together and is going to complicate things. So here's an example of one partition in maximal clicks, click 1, 2, 3, 2, 3, 4, and 3, 5. So you write this in terms of these potentials. All right. I mentioned a lot of these things are very much related with physics and in particular statistical physics. So this distribution, the most normal way to do this is to write it in terms of energies affiliated with each click. We already have seen this before. So here basically each of the potentials is written to what form? E to the minus c, where E is an energy defined over that particular click, and because the product, basically you get a Gibbs distribution where the energy of the system is the sum of the energies over maximal clicks. Okay, so this is the potential defined over each click. Now, this comes with different names, right? As we will see in some books, they say, oh, this is a maximum entropy type of distribution. In machine learning, they call this energy models. At the end of the day, you can even think of this as a trick, right? Where there's no energy or something like that, but you write these potentials e to the minus exponential, because that way you guarantee that you will get a positive product that fits well with the fact that this is a distribution, right? So writing a probability as e to the minus energy, it doesn't have to be motivated by physics. All right? So this is a parametrization that only accounts for pairwise potentials, all right? Now, you may say, but this is not maximal clicks, right? So I can see here potential 1, 2, 1, 3, 2, 3. So as I said, you can actually do anything you want here because this factorization is not unique. So here you use pairwise potentials. Okay, so here is the very general way of parametrizing these potentials on clicks, and this is what is called a log linear model. So each potential, you write it as the log of each potential to be a set of some basis functions defined over the features yc. So these are the variables in the click, dot product with some set of parameters theta c. All right. So this is a linear model, right, in statistics. So the log potential is expressed here as a linear model. Now, in a general problem, the two tasks that you need to perform is you may have to ask yourself, what are these future functions here, phi? Okay, and sometimes you just heuristically you assume something, all right? In other type of models, in, for example, language models, you're going to have to learn these future functions, or you can, you can envision throwing lots of these functions and letting the data figure out which ones are needed. And the second problem would be to calculate those parameters theta c. And we will see that's where the concept of stochastic optimization will come in the way these parameters are computed. So so remember, this is the log of its potential over a maximal click. All right, so the potential is e to this linear term here. So if I take the log of the distribution, so this distribution is the product of all the potentials. So the log will give me the summation of all of these logs. So I'm going to have the summation of all of these future functions times theta c defined over each click, minus the normalization factor z of theta. Okay? And again, you see that this animal here, z of theta, is going to be coming in all the time, and it's going to be a headache because it's not like, okay, this is proportional to that, we don't need this. So unfortunately, if you're going to estimate these parameters, all these parameters are coupled through this normalization term. Okay? So for example, when we try to do, let's say, maximum likelihood estimation or map estimation, you can envision, if you write this, if you try to maximize this, right, and you do MLE, this term is going to be difficult to compute because it will require integration basically on YC of all the product of the potential, so that would be a very difficult term to operate. All right, so one example, if these future functions are, if we work with, so we work with a pairwise Markov random field. I forgot to mention that Markov random field is basically the alternative word that goes for these undirected graphical models. So we only take pairwise potentials, and we assume that each of the variables can take k values. And so these future functions are basically indicator functions. So in this case, this particular indicator function takes the value 1 when the variable ys is j, and the value yt is equal to k. Okay? So, so effectively you can think of this, a future vector of length k squared because you have k times k variables. Okay? So the potential basically can be written as a table, because if you try to calculate the potential for values of ys and yt equal j and k, so effectively what you need to do is, you can see that this is the exponential of the jk parameter theta st. Okay? So in some sense, there is a similarity between, for this discrete model using tables and using this log linear model, but obviously the log linear model is way more general because we can put any sort of future functions we're interested there. All right, so we can bypass this. So here is, for example, in English spelling, all right, if you look at the document and you try to create future functions that involve 3 words, okay, so for example, this, can be an indicator function over 3 words. T is an index in the text, okay. Theta k are the corresponding parameters, all right? So this function is a binary function, can take the value 0 or 1. So this way you can identify certain words. So if you have, for example, this is for triplets, so if you have a word ing or, or something similar, the only problem is if you try to do this for a real text, right, and you take, 26 letters in the alphabet, so this will result basically to 26 to the power third parameters theta, so it will be computationally a very difficult thing to do, all right? So it's not like you're going to populate tables with millions of parameters and you're going to do sort of MLE to compute that. So this will not work very well. Okay, so now I want to go back to and slowly to the Ising model and revisit basically some of the ideas we discussed and see how we can train this model with stochastic optimization. All right, so the Ising model, we're looking on a grid in 2 dimensions or 3 dimensions. We're basically trying to mimic the behavior of magnets. So these variables are binary variables plus minus 1. You can think of this spin up, spin down type of things. When neighboring spins basically are in the same direction, you get what's called ferromagnets. When they try to align in opposite direction, you get anti-ferromagnets. Sometimes you get part to be behaving this way, part to behave that way, and then in some sense you have a phase transition. Okay? You may think this is a toy problem. It's a very difficult problem, and some of the references that I posted actually, not surprising, they're like from the last 5 years, okay? Because if you can do this problem properly, there's millions of applications in many different areas. And of course in machine learning alone. Okay, so the parameterization for the model, so the potentials look like this. So we're looking here at the pairwise potential. Obviously, each of these variables can be spin up or spin down, so plus minus 1. All right, so it's on our table, each of those values, we're going to write it as e to w and e minus w. We use the same w basically to describe all these probabilities. And this w is going to be an unknown parameter that somehow we have to compute or assume. You remember in the context of the energies that we used before, right? What is the local energy here for the system? You remember we wrote the log of the potentials to be of what form? I mean, the potential basically we wrote e to the minus e, right? So what's the energy here? Sort of energy. Minus w, all right? So if w is positive, all right, you know from your undergraduate physics, the system would like to go to low energy, okay? Low energy means high probability. So, if can you tell me from all of this, looking at this table, which situation will give you then the low energy? So take the w is positive, and you told me the energy is minus w. So if w is positive, which configurations are going to give you low energy if w is positive? Remember, this is the configuration, both are plus 1, this is both are minus 1, this is plus minus 1, plus minus 1. So which configurations will give you the lowest energy and the highest probability? If the energy is minus w. Remember, low means minus 100 is lower than minus 50. Or 0, or 10. So which configurations are going to be favored in that case? The diagonals, which means either they are both plus 1, spin up, or they are both down, spin down. So basically the system will try to give you the same arrangements of the spins throughout the lattice, okay? And of course you get the opposite effect when w is negative, okay? So in a trivial sense, if you make WST constant, okay, you can get sort of a simple, the most obvious version of this Ising model. All right? So we discuss all of this. Here's the difficult thing, because I mentioned that the normalization constant for this, Markov random fields is the headache. So in general, to compute the normalization term, even for the Ising model, is NP hard, okay? And actually, I was looking at it this morning. You can look at the review paper published in Science News, 10, 15 years ago, that basically gives a proof on how difficult it is to compute the normalization in a simple two-dimensional Ising model, okay? So yeah, if your Ising model is 5 by 5, you can do it by hand. 10 by 10, you can do it by hand. Try to do it in a million by a million, okay? That's a very difficult, complicated fix. There is a relation between the Ising model and Gaussian graphical models. We actually, you maybe forgot, but somehow in some of the examples we use these ideas. So if I take in the Ising model pairwise potentials, all right, so I can write this as this, all right. So the log of my distribution is minus the summation of these terms. Remember before I had e to the w or e to the minus w, I still have the same thing because these y variables are plus minus 1, okay? All right? So basically, this is like summing all the energies of these terms over the pairs, and if you want to write this in a matrix form, all right, you will put 1/2, so because this is an undirected graph, you don't account the interactions, let's say, of nodes I and j to i's, okay? So immediately you can see that this looks like a Gaussian Gaussian graphical model, all right? But obviously we will need something to mimic the mean term, and the way you do this is by introducing an external field in the energy function that looks like this, okay? The external field you can think physically if you, in this magnet model, right, is maybe you want to control the average magnetization of the system, okay? If this is a composition of a material system, an alloy, you can control maybe the average composition. This can be related to an external magnetic field or something like that. So in the context of what we do is we basically enhance the energy with this term beta transpose y, and immediately you can see if you plug things together and you complete the square, you can pose this Ising model as a Gaussian graphical model, all right, where the relation between variables is basically direct. So the precision for the Gaussian model is basically the strength of these links that you got on the MRF. The mean is given like that, and the constant, is your standard. Here's a complication. In a Gaussian, if you have a multivariate Gaussian, we mentioned the normalization is a problem, right, for the Ising model. So if somehow we can turn this problem, in this case, to a Gaussian, we know the normalization actually is very easy, because the normalization for a Gaussian is the determinant of 2 pi sigma. And you can do this in d dimensions with a cost that goes to d cubed. Well, unfortunately, in the Ising model, right, if you have d, you have, let's say, d pixels, and each of them can be plus minus 1, you're going to have to sum to find the normalization over 2 to the d power, values, okay? And this is where I mentioned that this is NP hard, okay? So Gaussian easy to normalize, the Ising model not very easy to normalize, very nasty. And of course, in many ways you will think of the Ising model being trivial, but the Gaussian is much more rich model, but we can see there is a complexity there. In the Ising model, you can generalize actually, and if you have a fully connected Ising model, all right? So all the entries in the W, not just pair potentials, but you have all the entries W, you get what is called a Hopfield network, and I think this was one of the early applications of probabilistic graphical models back in the 70s or 80s, all right? And I'm going to give you only an example of what this is. So in this Hochfeld networks, basically, what you do is you provide a lot of training images, all right? And so you train the system, so you learn all the parameters in the system, and then somehow you provide the same training examples but with lots of pixels missing. So it's like, your brain doesn't remember everything. I look at a given person and I say, what is his name? Who is that person? Right? Because my brain cannot take all the pixels and process them. So the idea here is you give these training images with lots of black pixels missing, all right? And then this Hochfeld network is trying to figure out to what it corresponds, and you can see this at the recovery images in some iterative stochastic optimization sort of version of these algorithms. And we will revisit, today or on Thursday these algorithms, okay? So, so this is sort of the imputation problem in this imaging, and that's why it's called associative memory. It's like, you already have memorized things, but, you want to be able to make fast decisions using incomplete version of these images and figure out what they are. Okay. All right, so the way that this, I'm not going to actually give you lots of details of this because we will do gradient methods to address these problems. The method that I indicated here, there are iterations basically to solve this problem. So the iterations are basically using a method that's called iterative conditional modes. Okay, and the iterative conditional modes are based on figuring out the most likely state of a node given all the other nodes. Okay, and this is the model in terms of a sigmoid function, and I can tell you this has an exact solution. I mean, if you think of an Ising model, right, and you want to find the state of a pixel, most probably, what the common thing to do is look at all the neighbors and say if they're all +1, then it has to be +1. Something like that. So in some sense, this is what this does. Okay, so there is an analytical solution to that problem. Of course, this has to be weighted with the strength of the interactions of the pixel S with the other pixels T. Okay. Now there is a much better solution, as I said, that we will discuss using gradient methods. This also goes, it's very much related to what's called recurrent neural networks. Boltzmann machines are basically extensions of these Hochfeld models where you simply introduce hidden variables in addition to what we saw up to now. Okay, so I'm going to say much more. And all right, so let me finish on this with another name that is very popular in physics, and it's called Potts model. Really, it's like the Ising model, but here you allow for multiple discrete states. So in case of 3 discrete states and the same strength of the bonds, basically J, the tabular form of these potentials looks like this. Okay, I can tell you, if you ask me, I can recollect 5 different problems that I came across using the Potts model when I was a graduate student. So this is a very important model in multiple areas. Okay, so I'm certain if you search on Google Potts model, you will come with 1 million basically hits. Okay, because there's lots of relevance. So here is so an application of the Ising or the Potts model basically, and I think you guys worked on the homework on this early on. What you see here is using different strengths, all right, and trying to find basically a map estimate or the lowest energy of the system. And you notice when J is very big, you get clusters that they're spin up. When J is very low, you have very small clusters. Actually, if you want to, now I remember one of the major applications of Potts models. If you want to get samples of polycrystal microstructures, this is how you do it. All right. So these things can basically, they're not nice spherical or smooth particles, but you can figure out. You say here's one grain, there's another grain, and another grain. So this is sort of something that can mimic a nucleation process, and will give you. If you run it again and again, it will give you different realizations of a polycrystal microstructure. Okay, so obviously somewhere in between for J, you have a phase transition, all right? And this is a very important area of research, trying to compute actually when the phase transition takes place. Not an easy problem. By the way, these are colors because this is a Potts model, right? So the intensity of the colors tells you what state you are. So it's not just black and white, but different colors. I think if you click this little library from Kevin Murphy's toolbox, you will see what's the corresponding K for this problem. All right. So let's discuss now more details on the Ising model. And I know you worked in the homework, but we really avoided discussing some sort of complexities of this model. So here, you can think this being the actual pixel values, can be discrete states. This is actually what I have in here, all right? These are the unobserved variables, okay? And they are defined over a grid. So a good way to model these Y variables is through an undirected model, okay? But then also you see observations of these nodes, and a very good way to describe these observations is through a directed model. So really what you have is, you have a mixture of an undirected model to describe basically the correlations on a grid of the Y variables, and then to describe the observations, you have a directed model, okay? So if you try to write the joint probability distribution, basically, and we already have seen this, you're going to capture these dependencies between the variables by factorizing these. This is the prior, basically, distribution of Y as a Markov random field, okay? These are potentials over edges, and then, of course, they're going to have these observations that are defined through a directed model. Okay, so when we did this in the homework, somehow I threw at you this term and I threw at you that term, but really we do not bother very much to emphasize that this is sort of an interesting new type of a graph, because obviously you're not going to capture the correlations in Y with a directed graph because it makes no sense in an image, right? So you're going to capture them with an undirected graph, but this really it is a directed model, as you see here. Y is the parent of Yt is the parent of xt. So this is the probability of observing xt, assuming that the true state of that pixel is k. Now, if you actually want to avoid complexities, what you can do is you can take this term here and lump it inside this clip potentials, and then actually work with an undirected graph and never bother with, and you remember we were doing this when we had these evidence potentials, we were lumping them on these terms, all right? So you can do actually the same thing and sort of avoid having to say that you have an undirected graph and then, a directed portion of it. All right? So this graph actually in the literature, when you have both a mixture of undirected and direct, is called a chain graph. I think somewhere I may have mentioned this in parsing in an earlier lecture. The model is really a 2D analog of a hidden Markov model, okay? And it's also called a partially observed Markov random field, okay? It's partially observed because you don't know the Y's, but you know the X's. All right, so an inference is a difficult problem, so we need to discuss on how to do this. Okay, well, I'm going to mention this, right, and maybe there are an example or two in the slides. If you take this model and your objective is to use it in a regression content, so you give an x and you try to compute y, so this Potts prior, in Potts prior is basically this, all right? This is a Markov random field. It's very appropriate on a supervised problem. But if you try to model this in an unsupervised context, this can go completely wrong because, for example, you can think this enforces smoothness as you pass from one pixel to another, but in real life, in images, you can have discontinuities and go from black to white suddenly, right? So in an unsupervised problem, this prior will not work, all right? So it's okay to use it here for the supervised problem, but it doesn't work for unsupervised problems. All right. Let me just finish on this with discussing about this Gaussian Markov fields, basically written in terms of precision matrices, not covariance matrices. So again, I have pair potentials here, and these evidence potentials, if you like, and you can parameterize them like this and like that. So immediately you can see, if your parameterization is given like this, you will get a Gaussian basically, but this Gaussian is going to be on an information form because it's written in terms of precisions, and this variable eta rather than the mean, all right? And so these undirected graphical models, they're written in terms of precision matrices, and in particularly because these precision matrices are sparse, we have sparse precision matrices versus sparse covariance matrices. Can you remember when did we use in this course a Gaussian representation of a random field where we had a sparse covariance matrix, and we did some Cholesky decomposition. And I believe you did this in your homework, like maybe homework 1 or 2. You remember somewhere you Suda gave you a homework on a Gaussian random field. It's in the notes, I know for sure, all right? But there what was happening is we worked with a covariance matrix, not a precision matrix. And a sparse covariance matrix is not the same as the sparse precision matrix, okay? Day and night. So this Gaussian Markov random fields lead to a sparse precision matrix, okay? The models we worked early in the course, they were leading to a sparse covariance matrix. Very different. Again, you may want to look on the notes. So obviously, you don't really know the sparsity of this lambda. So here we use pairwise potentials. So in essence here, if this term is 0 or not, it implies if there is link between two nodes or not. So in essence, learning the values of lambda is the same problem as learning the structure of the graphical model. Okay? So you can pose this as an optimization problem where you learn the structure of the problem, of the graph. All right. So let me, I'm going to give you an extension. So we discuss on this, Potts model. We have the Markov random field for y, all right, and then we had an observation model that can be anything. Basically, it can be a Gaussian or something like that. So I'm going to give you a picture, and I want you to look at this picture and tell me. So this is time. All right, and All the other links are basically, let's say, in space. So I want you to tell me what exactly you see when it comes to the context of the links on this image. So first, let's concentrate on how the variables change in time, okay? So if I look, let's say, at a given time, the variables depend on what things from the past. So I mean, I'm looking here, it depends on t minus 2, but also it depends on t minus 3. All right? So, so basically, the structure in time looks like this. All right? The probability of yt specify given yt minus 1 and yt minus 2. And so these matrices that you see here define the sparsity of the connections in time. Okay? Now you notice also, and again, this is sort of in 1D, but you can think of these variables being on a grid. The dependence at a given time between the y variables, what do you think, how do you think they're being done? If this was an evolving image, let's say in a video, right, and these were instances of the videos at different times, so the pixels at a given time, how are they correlate? How are you going to correlate them? With a directed graph, undirected graph. So obviously in time you can see we have a directed graph. All right? But how are you going to correlate the pixels at a given time? With a Markov random field, basically. Okay? So effectively, A1 and A2, they're going to define the sparsity of the evolution of y's in time. Okay? The sigma, or precision if you're going to use it, depending on how you do this Markov random field, they're going to define the correlations at a given time in space. Okay? So there is sparsity in the dynamics, but there is sparsity basically in capturing the correlations for a given time. All right? So there is this dynamic probabilistic graphical models actually is a very hard area of research, and there is a very recent book, if anybody is interested, to look. It's it's in press, but I have a copy of it, for review. So if anybody is interested, you can let me know. It's, I think, 700 pages of very new algorithms for doing this type of problems. All right, don't need this. Okay, and I have to go now to slide 65 so we can do maybe some of the training. All right. All right. All right. So let's go back to this log linear model. At least we can start the discussion on this. So we write this probability of y given theta. You remember each of the click potentials is e to the theta transpose some future functions defined over the click C. So the total distribution is written like that. We agree? Right. So our objective is to find the parameters theta, and we're going to do sort of a trivial calculation to start with. We're going to do maximum likelihood estimation. And I think once you know how to do MLE, to do basically a map estimation is nothing but to put a prior there and do the same sort of calculations. Okay, so what we're going to do is we're going to collect a bunch of data, so n data points. So these are my observations yi, okay? And I'm written here this scale log likelihood. I put this factor 1 over n there because it's going to simplify the calculations I want to do. So do you agree that the scale log likelihood looks like that? So this again is log likelihood, all right? So when you take logs, you're going to get a log of this partition function here, all right? And then log exponential will disappear, and you will get the summation of this, and then summation over all the data points. All right? The form of this equation, by the way, it is very general. It appears in infinite settings in machine learning, but here the difficult thing is you have these local parameters, and you can envision an algorithm where you update these parameters locally, but unfortunately this time it basically messes you up because it links all the parameters. Since this, to compute this partition function z, basically you have to solve, as we will see, an inference problem. You have to compute, you have to link basically everything together, okay? So this is not good, all right? So we need to find some way to handle this problem, okay? So let's see what is going to lead. You remember this distribution form? It looks like an exponential function type of distribution. So if we haven't proved it on this semester, it's in the notes from the course last semester, so you can look at it. Basically, the likelihood is a convex function of the parameters. So it has a unique global maximum, so that's good news. So we know there is a solution if we want to do an MLE. I mean, this is of concern, obviously, because if you have some partition function z of theta, who knows what happens, right? It's not guaranteed that it will give you a convex function, but because of this exponential family distributions, you get a convex function. All right. So we take derivatives with respect to the parameters. Now, if it's click, so theta c are the parameters that define the local potential on click C. So let's look back again. What will you get from this term when you take derivatives with respect to theta c? You will get the future functions c, right, at each yi, okay? All right? So this is what you get. And then from the second term, you will have basically to take derivatives with respect to theta c of the log of z. Okay? All right. Now, there is a proof that I did not have time to type it. It is literally 2 lines, so you can go home and do the exercise. You can actually show that the derivative of the log partition function with respect to the parameters of click C, it is nothing else but the expectation of the future functions phi c with respect to the underlying probability of P of y. This is no approximation or anything. So you remember if you think the distribution being the product of this potential, so you have logs, so you're going to get summation of each of these terms, and only one of these terms will actually give you what the parameters theta c. So effectively, at the end of the day, it is the expectation of the future function phi c, and you remember is this function phi c that's affiliated with theta c, all right? So you get the expectation with respect to the underlying distribution. So you notice here there's no evidence, right? It's P of y given of theta, and so it's a very difficult calculation, right? You have to find this expectation, and to make it worse, you have to find this expectation at each step in the gradient descent algorithm. So it's not like you're going to do it once and you're done, because this involves the parameters theta, and that's what we're interested to compute. So you're going to have to do iterations for that. Okay? So, but let's see something extremely interesting that comes out of this. Okay? So, if you trust me that this is the expectation of the future functions phi c with respect to the true distribution P of y, all right, so I'm writing this in notation of expectation. And the first term, all right, okay, hopefully I don't think I have missed a 1 over n here, so I don't know if the 1 over n disappeared there, okay, and this is outside the parentheses, so you guys check it for me. So this is 1 over n times the summation of the future functions phi c computed at each data point yi. So this is what you get from the first term. So look at this and tell me in a more compact notation, what is that? So 1 over n times, so you have a data set, n points, and you compute this future function c at all the data points. So what is that? It is the expectation of phi c of y with respect to what distribution? Nope. Remember, yi, right, are samples that came out from this distribution. So when you have the samples, you have an approximation of the distribution. How do we call the distribution with delta functions? It's Monte Carlo type thing. What's the name? So we took, right, n samples from this distribution. So here's one, another one, another one. All of the samples in approximation of the actual distribution. How do we call it the approximation? Defined in terms of samples. Empirical, thank you. Why are you going down there and hiding, you know? You almost, you know what? You will become worse than Yin Hao. If you couldn't, you will put your head under the table and who knows what he does there. Okay? If there was sand, there was, dig in the sand, put his head. So this is the expectation of phi c with respect to the empirical distribution. Okay? So basically the gradient with respect to the parameters theta c is the expectation of phi c with respect to the empirical distribution minus the expectation of phi c with respect to the exact distribution. So basically, if you set this, do gradient optimization, you say we do a low estimate, right? In this case, you set this equal to 0, and basically we have a problem that we were discussing in the last 3 or 4 lectures. And that problem is what? It's really moment matching. You see that? So the expectations of each of these future functions for each click, right, needs to match the corresponding expectations under the empirical distribution. It's a very easy way to implement actually this, okay? So effectively you have to set this equal to this moment defined for the under the empirical distribution. Okay? So again, this is for the MLE estimate. You can extend this to a map estimate quite easily. Obviously, you can do way better than MLE. You can employ stochastic optimization. I have 1 minute. I don't know if we have time. So let me just, we will come back to this problem obviously on Thursday, but let me tell you the starting point. So what about if in our problem, we said we had observations yi, but how about if there were hidden variables in the model? Let's say that we call them H. How are we going to compute the parameters theta when there are variables that actually we don't know what they are? So it's not like we're going to find the empirical distribution of H. There's no data on H. Okay? So obviously, if that is the case, what you need to do is you will need somehow to, when you define the log likelihood, you will need to integrate the H variables out. Okay? You will need to integrate the H variables out. And what comes out, that when you do the calculations, this integration in H looks very similar conceptually and mathematically like computing the partition function where you integrate it in Y. So effectively, these terms that you get, they look like partition functions computed not at arbitrary Y or integrating over Y, but with Y fixed and integrating in H. But they are still like partition functions. And I'm going to give you the answer, and then we'll come back to it at the end of the day. So the answer comes basically that the gradient with respect to the parameters theta c is there is a summation in the hidden variables, so you integrate those out, and basically it's the difference of two expectations. One of them is under the empirical distribution of expectation, empirical distribution of y, and the other one is actually the actual moment. So there is sort of moment matching here with h integrated out, okay? In one of the moments, y is basically integrated out, in the other moment, y is fixed, okay? Y is fixed. And this has lots of sort of implementations based on expectation maximization. Actually, what is called with the name generalized expectation maximization. So we will go back to this on Thursday, and then we will give a stochastic gradient descent sort of approximation for this type of problems.